This video is on a method called variation of parameters, which is appropriate for solving non-homogeneous second-order differential equations. The second part here, how does it work, goes through a long example about how to solve this. I'll let you read that at your leisure. What I want to focus on is the shortcut approach, which is described in part 3 here, and that is that you will find some u1 and u2 prime that is related to y1 and y2. Those are your solutions to the homogeneous equation. G is the right side of the non-homogeneous equation when it's put into its general form. And W of t is the Wronskian, which is presented in the existence and uniqueness video for second order equations. You'll see all three of these elements as we progress through examples. So let's start looking at example number 1 here. Which asks us to solve the equation y double prime plus 2y prime plus y equals 3e to the negative t. So this is non-homogeneous because the right side is an exponential function. It is not 0. Remember, homogeneous equations are if your differential equation equals 0. In this case, it doesn't. It's already in its general form. And from here, I see that this part is our g of t. So I want to know, what are the homogeneous solutions? Which means I want the characteristic polynomial, which is r squared plus 2r plus 1 equals 0. This happens to factor into r plus 1 quantity squared equals 0, which means we have r equals -1 twice. And that means that I'm going to say our homogeneous solution is of the form c1 plus c2t e to the negative t, which means that if you multiply through, you'll have y1 as e to the negative t and y2 as t e to the negative t. So these are our two homogeneous solutions. So we have our g, we have our y1, y2. Now we need our Wronskian. The Wronskian is given by the determinant of our homogeneous solutions and their derivatives. So y1 is e to the negative t. Its derivative is negative e to the negative t. y2 is t e to the negative t. And its derivative is e to the negative t minus t e to the negative t, and that was obtained using the product rule. The determinant of this is multiplying the diagonal, so that is e to the negative 2t minus t e to the negative 2t minus, now multiply the off-diagonal element, so that is the negative e to the negative t times the top right, t e to the negative t, which is going to be negative t e to the negative 2t. And when you simplify, you're going to have a minus t e to the negative 2t plus t e to the negative 2t, so those disappear. And we are just left with e to the negative 2t. This brings us to u1 prime is equal to negative y2, which is t e to the negative t, times g, which is 3e to the negative t, over the Wronskian of e to the negative 2t. And this simplifies to negative 3t. When you integrate, what you get is that u1 is going to be negative 3/2 t squared plus c1. And when we look at u2 prime, that's going to be positive y1, which is e to the negative t, times g, which is 3e to the negative t, all divided by the Wronskian of e to the negative 2t, and this simplifies to 3. When you integrate that, which happens to be very nice, u2 is going to be 3t plus c2. And finally, the full solution, our general solution, is y equals u1, which is negative 3/2 t squared plus c1 times y1, which is e to the negative t, plus u2, which is 3t plus c2, times y2, which is te to the negative t. And that is our final solution. There is some simplification that could be done because you have a t squared on the left, you have a 3t times another t, so a t squared on the right, but it's not a required step. And there's our answer. Let's take a look at another one. Notice, by the way, that the particular and homogeneous solutions are all present, all at one step. Now we're going to take a look at number 2. Number 2 only asks for the particular solution to the given equation. Notice that this equation is not in its general form because the y double prime is multiplied by a t squared, not 1. So the first thing that I'm going to want to do is to put it into its general form, which is going to be y double prime minus 4 over t y prime, as after dividing by t squared, plus a 6 over t squared y equals 4t. So that's the first step in my mind. We also are given the homogeneous solutions, so we don't have to try to find them, which would be challenging anyway. And so we know that one solution is t squared, the other t cubed, which means that the Wronskian will be found as follows. So again, I tend to put the top row as my homogeneous solutions, the second row as the corresponding derivatives. Then when you cross multiply, you've got t squared times 3t squared, which is 3t to the 4th, minus, now cross multiply the off diagonal, you've got 2t times t cubed, which is 2t to the 4th, and we are left with a single t to the 4th as our Wronskian. And now we could jump to finding u1 prime and u2 prime. So u1 prime is the one with the negative in it, so negative. We've got y2, which is t cubed, times g of t. Remember, g is this right here, the 4t. It's the right side of our general form. So that's going to be 4t, all divided by t to the 4th, or Wronskian. So the t to the 4th powers disappear, and we've got negative 4, which means that u1 is going to be negative 4t plus c1. Let's look into u2 also. So u2 prime is going to be t squared times 4t over t to the fourth. And that's going to give us, we have a 4t cubed on top with a t to the fourth on the bottom. So 4 over t, which when you integrate, we have u2 is 4 times the natural log of t plus c2. Now c1, c2, when you actually bring into your general solution form, it's going to give you the particular and the homogeneous. So the particular part really stems just from the pieces without constants. I'm going to focus on that. So yp, just the particular solution, is going to be given by u1, which is negative 4t. I'm dropping the c1 again because I don't want the homogeneous part for this problem, since it only asks for the particular solution. So negative 4t is u1 times y1, which is t squared, plus u2, which is 4 times the natural log of t, times y2, which is t cubed. And if we want to simplify a little bit, which we can, I see that there's going to be a t cubed on both sides and a 4 on both sides. So I'm going to factor out a 4t cubed. And that is going to leave me with a natural log of t minus 1. So that is our particular solution. Let's take a look at problem number 3 here. It asks us to solve the second order equation, y double prime minus y equals 2t plus 4. So now here we're starting from scratch. First thing I want to do is get the solution to the homogeneous equation. So first step, I've got r squared minus 1 equals 0, which means r is going to be plus or minus 1. And so I know that the homogeneous solution is going to be of the form c1 e to the negative t plus c2 e to the positive t. And I am going to call this one y1 and this one y2. It's already in its general form, which means 2t plus 4 is our g of t. Now I need our Wronskian. We have e to the negative t and e to the t again as our two solutions to the homogeneous equation. That means that the derivatives are e to the negative t and e to the t. When you get the determinant, you're going to have e to the 0, which is 1, minus a negative e to the 0, which is going to be negative 1. And this works out to be 2. You have to be careful, because if you lose a negative sign or do something else wrong, you may get 0, which is a bad sign. But in this case, it shouldn't be 0. Finally, we could start putting together the piece of information that we need. So u1 prime is negative y2. y2 is e to the t based on how I chose my y1, y2. gt is 2t plus 4. And the Wronskian is 2. This becomes negative t plus 2 e to the t. So we want to integrate this. U1 is going to be the integral of negative t e to the t minus 2 e to the t dt. The first one you could solve with, let's see, integration by parts, or you could use the tabular method if you are familiar with it. I'll go that route. So I know that our u portion is going to be negative t, then negative 1 taking its derivative, and 0 taking the next derivative. The dv portion is going to be e to the t. When I integrate that, I get e to the t, and if I integrate again, I get e to the t. Then you start multiplying diagonally downwards. First one is going to be positive, the second one negative, and so forth. And so what this gives me is negative t e to the t minus negative 1 times e to the t, which is going to be positive e to the t. That is just the derivative of negative t e to the t dt. We also are integrating the second term, which is minus 2e to the t plus c1. So a little bit of simplification can happen here because you've got 1e to the t minus 2e to the t's. So we've got minus te to the t minus 1e to the t plus c1. And if you wanted, you could factor an e to the t in the first term. It's not a necessary step at this point. Now let's take a look at u2. I'm going to do that up here. So u2 prime is y1, which I chose to be e to the negative t, times 2t plus 4, which is our g function, all over 2. This is going to be positive t plus 2 e to the negative t. Now we want to integrate this. So u2 is the integral of te to the negative t plus 2e to the negative t dt. Again, we could use the tabular method. I'll put this on the far right here. So I've got my u's and my dv's. U, I'm going to choose for the first term to be t. Its derivative is 1, and that derivative is 0. That means dv is going to be e to the negative t, and its integral is negative e to the negative t, and when I integrate that, it becomes a positive e to the negative t. Then I start cross-multiplying, and what we get is a negative te to the negative t minus 1 times e to the negative t plus the integral of 2e to the negative t, which is minus 2e to the negative t plus c2. And if we combine some of these terms, we are going to get a negative te to the negative t minus 3 e to the negative t's plus c2. Just to keep track of what we have, this is our u2. Here's our u1. So those are what we are going to be pulling in to our final solution, which I'll squeeze in over here. So y is going to be u1, which is, let's see, I'll write it as negative t plus 1 e to the t plus c1, that's u1, times y1, which is e to the negative t, plus u2, which is going to be negative t plus 3 e to the negative t plus c2 times y2, which is e to the t. When you multiply through by the e to the t, e to the negative t, you'll see that the e's, the exponential terms multiplied by the t functions disappear because they're going to become e to the 0, and you're going to have the homogeneous solution in there. I'll leave it to you to simplify on the side, but this gives you your final general solution. There is one more problem to practice here. This is number 4. We have another equation that is not in its general form, so we'll have to do that. And we are given homogeneous solutions. So let's start working through this. We want to solve this equation. Its general form is going to be y double prime minus a t plus 1 over t times y prime plus a 1 over t times y equals a t squared over t, which is t. So that t is our g function. Our Wronskian is going to be comprised of e to the t, which is one solution, t plus 1 is another. The derivative of e to the t is itself, e to the t. Derivative of t plus 1 is 1. When we get the determinant, we're going to have e to the t minus t plus 1 e to the t. I see that the e to the t's are going to disappear, and we are going to be left with a negative t e to the t for the Wronskian. Finally, we could start putting together our u's. So u1 prime is negative y2. y2 is t plus 1. G is t, remember, from the general form. And we have negative te to the t as our Wronskian. So the negative signs cancel out, the t's, the standalone t's disappear, and we are left with t plus 1 over e to the t, which is the same as t plus 1 e to the negative t. In the previous problem, let's see. Nope. I thought the previous problem had one exactly like this, so it's not quite as direct, but we could work from scratch anyway. So let's go ahead and do that. I'm going to set up the tabular approach in order to integrate this. So u, I'm going to say, is t plus 1. Its derivative is 1, and the next derivative is 0. dv is the e to the negative t, which has an integral of e to the negative e to the negative t. And the next integral is positive e to the negative t. So that when we actually integrate, we get u1 is negative t plus 1 e to the negative t minus e to the negative t plus c1. And this simplifies to negative t plus 2, e to the negative t plus c1. Now let's work through u2. u2 prime is going to be positive times the y1 solution, which was e to the t. Then g is t, and we are dividing by negative t e to the t. This works out very nice to just be negative 1, which means our u2 solution is going to be negative t plus c2. Which brings us to our final solution of u1, which is negative t plus 2 e to the negative t plus c1 times y1, which was e to the t, plus c2, or u2, excuse me, times the second solution to the homogeneous equation, which was t plus 1. And again, you can multiply through and combine like terms to simplify, but this is our final solution. As always, I leave a few practice problems for you to do on your own. Feel free to contact me if you have questions about them or want to check your answers. And that is the variation of parameters method.